Earthquakes are daily natural events that still offer a unique challenge to those trying to track them. Earth's crust is made from several vast jagged slabs of rock called tectonic plates, each rather than a hot, partially molten layer of Earth's mantle. This causes the plates to spread very slowly, at anywhere from 1 to 20 centimeters per year, but these tiny movements are powerful enough to cause deep cracks in the interacting plates, and in unstable zones, the intensifying pressure may ultimately trigger an earthquake. Luckily, because some of these forces occur at largely constant rates, the behavior of the plates is somewhat cyclical. Today, many of our most reliable clues come from long-term forecasting, related to when and where earthquakes have previously occurred. One of the most challenging aspects of studying earthquakes is obtaining observational constraints. Of course, it would be as easy as just looking deep down into the earth, which is at least 3 times deeper as anyone has ever dug. Instead, seismologists rely on the information gleaned from the few available types of data, the most important of which is the record of seismic waves. During an earthquake, sudden crustal motion excites elastic waves that travel through Earth and are observable at seismic stations on the surface. So, when do earthquakes occur? More precisely, what long-term and short-term processes trigger them? An equally important question and a fundamental challenge to the science of geophysics is, what happens during an earthquake? That is, what are the forces and motions during a seismic event? So, let's jump into the physics. The long-term processes. The strain change associated with large earthquakes has been estimated using geodetic and seismological methods. The corresponding change in stress, called the static stress drop, is about 1 to 10 megapascals, which is smaller than the several hundred megapascals needed to break intact rocks in a lab. Dividing the strain change by the strain accumulation rate suggests that the repeat time of major earthquakes at a given location are about 100 to 1000 years on a plate boundary, and about 1000 to 10,000 years within plate. These values agree with what had been observed at many plate boundaries and interiors. Here, we can observe the development over time of stresses that generate earthquakes. In an ideal case, the graph will show like A, although the stress accumulation rate is not uniform over time. B offers a more realistic version of the process that includes complications of variable strength, loading rate, and stress drop. The short-term processes. Earthquake fault motion can be viewed as frictional sliding on a fault plane. The friction changes as a function of slip, velocity, and history of contact. An earthquake can occur only if friction decreases rapidly with slip, a process referred to as slip weakening. If friction increases with slip or does not drop rapidly enough, slip motion either stops or occurs gradually. Here, we can see the slip distribution on the fault plane of the magnitude 7.3 1992 Landes, California earthquake. If you are interested in the details, pause the video in the next box. Rupture dynamics and energy. The stress time histories obtained through rupture patterns are complemented by measurements of such integrated quantities as the total radiated energy ER and the seismic moment MO, which gives the total amount of slip. Ultimately, one needs to consider the energy budget for an extended fault zone, but a relatively simple spring system nicely elucidates how energy is partitioned during an earthquake. The energy budget of earthquakes provides more insight into the stresses occurring in fault zones. This graph shows the observed ratio ER over MO, which specifies how much energy is radiated from a unit fault area per unit slip. Given the definition of MO from the first box, we can write this. For the whole obtention of this equation, please pause the video in the next box. So, summarizing, in the self-organized system just described, a small stress perturbation can trigger a seismic event. The growth of the earthquake is controlled by friction on the fault, which in turn may be affected by nonlinear processes involving lubricated dynamic slip. This growth process results in the standard magnitude-frequency relationship with occasional unusually large earthquakes, possibly caused by large runaway events. Various ideas for a better control in earthquakes are: elastomeric lubrication in a thin fault zone may change the roughness of the fault plane, and thereby change the frequency spectrum of the ground motion. Strategies for designing structures that will withstand ground motions from large earthquakes will have to account for this change in frequency spectrum. Understanding these processes is key to a better understanding of seismicity, rupture dynamics, and ground motion characteristics, which will lead to effective seismic risk mitigation measures. You can find the references and disclaimer in the description. This video is a submission to the final round of the International Applied Physics Olympiad 2021.